Hello. In a previous video, we discussed the theoretical aspects of differentiation of vector functions, so how it is defined and how the derivative is calculated. Now, in this video, I want to talk about the interpretation of the derivative. And here it is useful to recall one of the interpretations of the derivative of a function from R to R. So let's say we have such a function, f mapping R into R, and at some point A, the derivative exists. Now, what does this mean? Well, you may recall from your first course in calculus that we interpret the derivative of a function from R to R as the slope of the tangent line to the curve with the equation y is f of x at the point A, f of A. And in particular, the tangent has equation y is f prime A, x minus A plus f of A. Now, this is a line in the plane, right? So we can write down a vector equation for this line. And in order to find a vector equation for the tangent, we need 2 points on the line, right? So we can take the point when A is equal to x, and we substitute it into the equation, and that gives us y is f of A. So we get a point on the line A, f of A. Now we can substitute any other value for x into the equation to get another point on the tangent, and we pick the point, we pick the value x is equal to a plus 1, right? And then we get y is derivative of f at A plus f at A. And that gives us the point a plus 1, derivative of f at A plus f at A. So now we have 2 points on the line, and therefore we can write down a vector form or a vector equation, right? So we can write this as a f of A plus t 1 f prime at A, and of course t can be any real number. Right. So the vector equation we've got over here, this equation describes exactly the same line as that equation over there, right? It is just an equation in vector form. Now, we can also write down a vector form for the curve with equation y as f of x. Right? The simplest way of doing that is to set x equals to r of t, where r of t is t f of t. And again, t can be any real number. Right. So again, the range of this vector function r of t gives you the graph of f. Now, what can we say about this vector function? Well, remember, we're assuming that f is differentiable at A. And clearly, this first component there is also differentiable at A. That means our vector function r is differentiable at A. So it exists, and we can calculate it, right? Remember, we just differentiate component y. So the first derivative will have derivative 1, and the second component will have derivative f prime at A. So now, if we compare the derivative of our vector function r at A here with our vector form for the tangent line over here, right? What do we notice? Well, what we've got over here, that is just the derivative of r at A. And that's just r at A. Right? So what does this tell us? It tells us that the derivative of r at A is parallel to the tangent line to this curve at this point r of A. So we've got this here in a picture. Right? So here we've got our curve with equation y is f of x, or alternatively, in vector form, equation x is r of t, t any real number. Right? And here we've got the tangent line, right? And we've written it in vector form, and here we've got the derivative. Now we've drawn the derivative here and interpreted it as a geometric vector, in other words, an arrow. Right? So here we should note, right? So remember, we have two different interpretations for a vector. Right? Either it can represent a point, and in this case we interpret r of a as a point, right? And in fact, r of t, for every t, gives you a point on the curve. Right? On the other hand, here it is useful to interpret the derivative of r as a geometric vector or as an arrow. Right? And it is the geometric vector or arrow with initial point r at a and terminal point r of a plus r prime of a. Right? So here in our picture, there's r of a, and there's the terminal point r of a plus r prime at a. Right? Now, in general, if r is a vector function defined on some open interval containing the real number a, and our vector function is differentiable at this a, and its derivative is not zero, then we interpret the derivative of r at a as a tangent vector to the curve, which is the range of our vector function r, right? And it's the tangent vector at the point r at a, right? And the line here, so the line consisting of all points of the form r of a plus t r prime at a, we call the tangent line to c at this point r at a. Right? So this is in agreement with the special case we considered earlier, and in fact, if you draw a few pictures, then one can motivate this quite well. Those pictures you will find in the course notes.